This is called a review of simplifying radicals because you learned this in grade 10. So it's just a review, and most of you pretty much have it figured out after those 10 minutes that I gave you to work on it. But first, before we do that, let's talk about what this thing is. What would you call this whole thing?
A radical.
A radical. Right. Okay, we'll put that in there. The whole thing is called a radical, and it's made up of some different parts. How would you say this if you were going to name that number?
2 root 3.
2 root 3, good. You could say 2 square root 3 if you wanted to, but most people will say 2 root 3 just because square roots are so common, you don't bother saying the square part. What part would you say the 3 is? That's the radicand. Radicand. What about the 2? That big 2 in the front. Coefficient, yeah. That's the coefficient there. And then there's one more arrow, and what's that arrow pointing at? Whether it's a square root or a cube root or whatever, what invisible number is in there?
2.
2. There's a 2 in there. It's invisible. Whenever it's a 2, it's invisible. But what do you call that number? I didn't hear it yet. Anybody know what it's called?
Square.
Starts with an I.
Index.
Index. Yes. It's called the index. What you learned with radicals last year, well, one of the things, kind of the main thing that you learned was how to simplify a radical. And this is how it works. We already did this on the board. You guys figured it out. But here it is. You take that radicand and you find the largest perfect square factor. If you're not sure right off what the factor is, remember, go to your list of perfect squares. 12, well, there's only 2 options, right, for 12, because there's only 1, 4, and 9 that are perfect squares smaller than 12. We don't use 1, so it's 4 or 9. So 12 is 4 times 3. And we're going to break the 12 down into 4 times 3. And then all you need to do is take the square root of the perfect square factor. That becomes the coefficient. So 2, which means 2 goes on the outside, 3 stays on the inside. This is relatively easy, right? Like, as long as the numbers are small. It can get tricky if the number's really big, and maybe we'll look at some of those later and kind of some strategies for working with really large radicands. But basically, just find the perfect square factor, take the square root of the perfect square factor. So here's another one. This says simplify. And this is actually already a mixed radical, but it's not completely simplified. Even though at first glance you might think it is simplified because it has a coefficient at a radicand. But the radicand here has a perfect square factor. What's that perfect square factor? 9. So this becomes 2 root 9 times 2. Now I have to take the square root of the perfect square factor, which means take the square root of 9 and it becomes the coefficient. So that actually looks like 2 and then 3 root 2. Wow. And then what's that equal to? Do you know? 6 root 2. So multiply the number that was already in front with the new coefficient to give you the simplified radical. How could you test to see, like check, to see if your work is correct?
Put it in your calculator.
Put it in your calculator. So can somebody put 2 root 18 into their calculator? And somebody else put 6 root 2. We'll see what you come up with. 8.48 for 2 root 2? Or sorry, 2 root 18? And what about 6 root 2? Same. So we know that it's right. However, we don't know that it's fully simplified, but we do at least know that it's equal. We need to look at the radicand and make sure that there's no perfect square factor for it to be fully simplified. But at least we know that that they're equal.
Why did you put brackets in?
I just put the brackets around the 3 root 2 so it didn't look like 23 root 2. So just to kind of separate the 2 and the 3. Here's another one. This one's a little different because it has a different index, right? The index here is a 3, which means it's a cube root. So if you're thinking about the instructions that I gave, change square root to cube root. Change every square to a cube. So instead of finding a perfect square factor, we're looking for a perfect cube factor. What are the perfect cubes? So the perfect cube factor of 16 is 8. So this becomes the cube root of 8 times 2. And then what do I do with the 8? Take the cube root of it. The cube root of 8 is 2. So this becomes 2 cube root 2. Don't forget to write that index in there. If it's anything other than a 2, it needs to be written there. This is the last one we're going to do, and this is different. But it actually works the same way. Here we have variables instead of numbers. But remember what we were doing when it's numbers. We're looking for a perfect square factor. We're going to do this in 3 steps. We're going to look at the x's, the y's, and the z's all separately. If we had a number in there in the radicand, we'd look at that separately as well. But we're going to split those numbers into their factors, one of which is the largest perfect square factor. So let's think of the perfect, I don't know what to call it, perfect x's.
X.
Is x a perfect square?
It can be.
X squared is a perfect square, right? X squared is a perfect square. What's the next x perfect square? X cubed is not a perfect square.
X to the 4.
X to the power of 4 is a perfect square. What's the next one?
X to the 9.
I'm kidding.
X to the 6.
X to the power of 6 is the next one.
Oh, it's just like 2. X to the 8.
Because, yeah, and then the next one would be x to the power of 8. And then x to the power of 10. What's the square root of x squared? X. What's the square root of x to the power of 4? X squared. What's the square root of x to the power of 6? X cubed. And then the square root of x to the power of 8? X to the power of 4. Right. You have to kind of know your exponent laws to know that. But if you think of, like, if you did something like x cubed multiplied by x cubed, what do you do with those exponents? Add them. So that gives you x to the power of 6, which is why we say the square root of x to the power of 6 is x cubed. You see that now? Okay. So if we're looking at x cubed, what is x cubed's largest perfect square factor?
X squared.
X squared, right. So what we're going to do with the x is change it into a x squared times x. X squared times x is x cubed, and x squared is a perfect square. Now let's look at the y's.
So we just don't leave it like that?
We're going to leave it like that because y squared is already a perfect square. So let's just leave it as a y squared.
So is
Z to the power of 9? Not a perfect square. 9 is a perfect square, but z to the power of 9 is not a perfect square. So what's the largest perfect square factor of z to the power of 9? Z to the power of 8, right. Because this is z to the power of 8 times z. Basically, you can always look at, you see the pattern? If it's even, keep it. because it's a perfect square. So if the exponent is even, keep it, because it's already a perfect square. If it's odd, subtract 1 from the exponent, and that gives you the perfect square factor. So 3 became 2, x squared times x. 9 became 8, so z to the power of 8 times z. You just have to take 1 less, because every even exponent makes it a perfect square. So now what I need to do is take the square root of the perfect square factors. So I'm going to take the x squared and take the square root of it. What's the square root of x squared? X. That goes to the outside. So I'm just going to cross it out because we used it. What about the y squared? That becomes a y on the outside, so I use that. And the other perfect square is z to the power of 8, and it becomes
4.
z to the power of 4, right. Because z to the power of 4 times z to the power of 4 is z to the power of 8. So we use that. And then I can see what's left on the inside. I have an x and a z. That doesn't look a whole lot simpler, does it?
No.
But it is. Because the radicand does not have any perfect square factors. And that's what you need for a radical to be simplified. So even though it kind of looks more complicated, it's not. When you look at what the definition of a simplified radical is that there are no perfect square factors in the radicand. So that's done.